Hello. This is a joint presentation by MathWorks and Qualcomm about deploying AI models with Simulink, with a focus on integrating edge AI with Qualcomm Hexagon hardware for ideal performance. My name is Christoph Stockhammer from the MathWorks, and with me today is Rajan. Rajan, why don't you quickly introduce yourself?
Yeah, thanks everyone. Thanks, Christoph. I'm Rajan Mistry. I'm Senior Staff Engineer, Tech Evangelist with Qualcomm. We work with the dev marketing team, enabling developers that want to build anything on top of Qualcomm technology, especially run AI workloads on device. We try to enable them with some of the tools we have. And love to share the work we are doing with MathWorks today here with you. So.
Thanks, Rajan. I support customers in all sorts of embedded AI workflows. They're basically porting their trained models to edge devices. And I'd like to start out with one example of a customer project we ran. That shows already the common theme of this presentation, which is making developer workflows as easy and smooth as possible. Right. So this was an automotive OEM. And it was about a virtual sensor application for cabin air mass flow. And there were challenges there were a few challenges for this team, like they had a pretty involved AI development cycle that was time consuming, and there was hand coding involved and all of that. And so when we supported them, we were able to significantly cut down their development time. Compressed the model, quantized execution on the ECU in this case. So this is like, I've been working in this field for quite a time now, and I see that this is one of the main challenges, not so much the tooling, but the ease of use of the workflow, to make the tools easily accessible for developers. So this is like already informs our agenda. So Rajan will kick it off with speaking about the developer-first mindset for AI deployment. I will then introduce the hardware support package that we developed together with Qualcomm for Hexagon DSP, specifically talking about AI deployment to Hexagon. And all of this is enabled via automated C code generation, so really automatically generating C and C++, in this case it's C source code from the models. Right, with that, I'd like to hand it over to Rajan.
Thanks. Yeah, thanks, Christoph. So I would love to share with you where Qualcomm is going and why we're working with partners like MathWorks to kind of enable the dev workflows. Mainly, if you think of Qualcomm, we come from a mobile chipset background, right? So we have SoCs that go into smartphones. There's a lot of IP and enablement that happens on those smartphones. There's a lot of NPUs for AI acceleration, and we have a dedicated hardware block for all of those workflows, right? Whether it's CPUs, GPUs, audio DSPs, compute DSPs, NPUs for AI workloads, and you name it. Enabling that has been a paradigm shift for Qualcomm for the last few years, because now we are taking the same enablement and kind of scaling that across different use cases, right? So taking from mobile, going to automotive, going to IoT, robotics, drones, and whatnot. So enablement for each one of those looks different, right? So developer workflow is different for an Android developer, to an automotive developer, to an IoT developer. So we, as a company, the focus has been to get closer and closer to the developer workflow, right? What that means is we are focused on open source, right? We use open source wherever possible, but also contribute to open source wherever possible, right? So kernel contributions, our newer platforms on day one have ASOP builds already enabled, upstreamed through Linaro and whatnot, conforming to standards, not just contributing to standards, but like working with partners like MathWorks and making sure we are enabling developers in their workflow, right? Without having to have the developer learn 4 different tools to enable running something on a Qualcomm platform, enable partners. That way, the end developer workflow doesn't change, right? And that's what some of the things that we'll be showing today kind of focuses on that. Apart from that, just standardized APIs, documentation, there's a lot of work that's happening in the background to enable a lot of these use cases. So that's just a mindset shift for Qualcomm. The main focus for us is always been AI and running AI on edge devices, right? And moving forward, why is that going to be important, right? So we truly believe AI is going to be the new UI, right? Think of all of these foundational LLMs that are now running on devices, and agentic AI is a hot topic for developers, right? How I was having conversations at the booth where app developers are not really sure how they can use these LLMs, but then maybe the apps themselves don't use the LLMs, but they feed into these LLMs, right? So think of a use case where you just tell your AI assistant, hey, book me tickets to Imagine Dragons concert on 2nd October in Snapdragon Stadium, for example, right? That AI agent will then go work with the apps and then book those, right? So the action is actually the app is not managing the AI model. The AI model is kind of, it's the other way around. So there's two ways of looking at these, and we feel AI is going to kind of enable a lot of those use cases for end users. We do see AI inference moving to edge devices a lot, right? And mainly performance and efficiency on edge devices, but also the main concerns are privacy and security. A lot of use cases are kind of really restricted in not being able to send data to the cloud for AI inference. That's those kind of use cases you really want to run these on device. And especially now with these foundational LLMs, based on the use cases, like we have all different form factors, right? Going from smartphones to automotive to laptops to IoT devices. A lot of these use cases can now run actually 7 to 10 billion parameter models on a Qualcomm platform. So we provide tools and SDKs to really optimize and quantize those models so that you can run them on device. So these have enabled a lot of those use cases for the end user, right? Making those a lot easier for end users to use. And that's what will feed into that AI is a new UI concept. So for Qualcomm, like I said, it's for us, a lot of compute on our SoCs is basically dedicated to the workload, right? So we have CPUs where you can run your apps. We have GPUs for graphics rendering. We have a Hexagon NPU. That's mainly what we'll be focusing on today. But we also have these ISPs, sensing hubs. So if you're processing sensing data, there's a sensors DSP, audio data is an audio DSP. So overall, the SoC is a lot more power and performance optimized because there is a dedicated compute block that is custom built to run these workloads, right? And for app developers, it's all abstracted up where they don't actually need to learn how to code for Hexagon. They don't have to learn how to code for the sensing hub. It's all abstracted out into tools and SDKs that they are already using. And Simulink is one example of that. So like I said, today we'll be focusing on the Hexagon NPU, right? It's a marketing slide. So you can find more information on the Hexagon NPU. It's basically dedicated compute block that can do AI workloads specifically for math operators, like scalar, vector, matrix operations. It's all power and performance optimized, where a lot of your AI workloads are not running on the CPU. They are getting offloaded on the NPU. So I want to quickly, before I hand it off to Christoph, I wanted to kind of briefly introduce a traditional app development workflow, what actually it looks like for app developers as they are kind of start to build and integrate AI into their applications. From left to right, you can see from data scientist to ML engineer, you would start with data collection, you would then train your model, you would then optimize, quantize your model, and then test if the actual accuracy works for your use case or not. And then once you're done with all of that, then you would actually, the app developer would look into integrating that on device, right? And that's where you would take that model, try to build and integrate it into your app, but then also deploy it on device and see if it's kind of quantized and working on device or not. So towards the end of it, it adds a little bit more complexity to actual deploying it on device. So this is kind of this shows the software stack of what is running on device, right? You have all different types of operating system from bottom to top. You have driver support, kernel support, libraries and services, different programming languages that are supported, AI runtime, so you have a model from TF Lite or Qualcomm's own QNN or something like that. All of those runtimes are there. And then AI frameworks, you have TensorFlow, PyTorch, Onyx, and Keras. So it adds a lot of these different layers for app developers to be aware of. And what we really want to showcase is like how all of this is made easier by kind of getting closer to the developer workflow, right? That's where like Christoph will walk us through a workflow which the app developer doesn't need to kind of worry about all of these libraries. They can use the tools that they are already using, in this case, Simulink, and just write code and deploy an Hexagon NPU, and they don't need to worry about this entire stack. So yeah, with that, it's all yours.
Yeah, thanks, Rajan. So I'd like to introduce one artifact of this collaboration between MathWorks and Qualcomm, which is the hardware support package for Hexagon DSP. So what is this about? The idea is to be able to design your algorithms at a high abstraction level in MATLAB or mostly Simulink. Like you design your system, your model, we're going to see examples of that. And then the idea is to use automated C code generation to basically deploy those developed algorithms to the Hexagon, right? Either with the real hardware or with the simulators that are available. And this C code is optimized for the Hexagon, so we're using the Hexagon SDK and the libraries associated with it to get the best possible performance. Now, the specific example that I'd like to highlight today is smart speaker audio processing application. It's also something you can check out at our booth later on. It comprises two components. The majority of the algorithm is actually, in this brown box, in this large brown box. And it's basically audio input processing, things like feature extraction, and then output audio processing, like equalizers, things like that. And our goal is to deploy those parts to the ADSP on the Hexagon, whereas also our smart speaker obviously contains an AI model. It's a convolutional neural network, and this one we want to offload to the eNPU for performance and energy regions, right? So this is the high-level idea of our application. And how this works, you bring your trained model, you bring your own model, typically from PyTorch these days, could also be TensorFlow or also in MATLAB potentially. And the exchange format is an Onyx file, so we can use this and then use the Qualcomm tooling from the LPAI SDK to convert this into a file format, specific file format, a model.eai file, which we can then integrate into our simulation. So the AI, it's not on its own. There is some, pre and post processing required. So there's a complete application, and we can take this complete thing, simulate it, test it on our development environment, on our laptop basically, and then go ahead and automatically generate C code for the Hexagon NPU. And this is, in a nutshell, what the hardware support package that we offer for download does.
So the hardware support package actually includes all the dependencies from Qualcomm side, Hexagon SDK, the QNN runtime libraries, and all of that. Developers don't actually need to download that separately and learn about them. It's just the HSP manages all of that for them.
Exactly. I'll show a video of the setup process later. It's simple, 3 steps, so that you get an idea, but we're heavily building, obviously, on the Qualcomm tooling there. Right, here is the 3 components that are contained. You know, the tool integration with the profilers is important. We simulate, obviously, the hardware itself, but the simulators as well. And finally, you know, the way to get there is code generation. We take advantage of optimization libraries, like the vector extensions and the hardware library from Qualcomm. You can do things like process-in-the-loop simulations, right? So to run your algorithm on the embedded processor, verify, you know, for example, numerical accuracy. And last but not least, we have many examples to get you started. So this really means our workflow becomes much simpler. We have a one-time setup effort, but this is not really an effort. It should be simple, right? It's just downloading the libraries, and then you configure your model to execute on the corresponding hardware, and then you can go ahead and do things like pill simulation or deploy your final algorithm as generated C code. Now, to give you an idea of what this really takes is, you know, you open up the add-on Explorer tool and you can search for the corresponding support package that I'm talking about. So this is this one. And you can install it from here. So this will be behind the scenes, you know, collect and download all the necessary files that you need from our end to make this work. And you know, the license agreement, it's clear, it's not a whole lot, so it downloads quickly. And then you can do this one-time setup step. No. Basically, this is the magic that takes care of all the correct library paths so that we know, you know, where the Hexagon SDK lives and things like that. So it's really only 3 steps. I'm going to quickly show this as well. So we have a download link for the Hexagon SDK. In this case, I've already downloaded it. Just need to point to the download location, validate that this is a correct version. And the next step is another step for the, if I'm interested in AI model deployment as well. Can same thing for the LPAI add-on. Also previously downloaded this already. And the final thing is, when I want to run this on actual hardware, I would need the Android debug bridge. I skipped this for now, but just the same, download it, point to the folder where it's downloaded, and that's it. So those are the 3 steps I need to take. That's all I need to do. One-time effort should only take a minute or so. And then I'm basically good to go. Right, as a first step, what you can do is check out getting started examples. There is quite a few examples, and there is an easy one with a filter algorithm that you can use for getting started. Right here, it's explained in detail there. Okay. Now, going back to the AI part of it, as I said, you know, we consume this ONNX files, or you know, the Qualcomm EAI builder consumes those, together with quantization information in a JSON file format, and produces this model.eai file. So this is, again, the common source of this is ONNX files that can come, for example, from PyTorch. And I'm going to run another video that steps through this specific demo of a smart speaker system that listens to voice commands, recognizes them, and based on the commands, you know, then triggers some sort of actions like increasing volumes, decreasing volumes, stopping the output, or whatever. So this is also, again, the example you can see at our booth. So this is done in Simulink. For those of you who don't know that, that's a development environment for you know, modeling algorithms graphically. So you basically drag and drop blocks and connect them, like in a flowchart manner. And we have 3 components. We have an input processing, an output processing, and some visualization component, like in the 3 areas here. We get some input signal that could comes from memory in this case, but could also come from a microphone or other peripherals. Then we have the actual speech command recognition system, which comprises a feature extraction part we need for the deep learning model. Then the actual deep learning component, which is a convolutional neural network in this case. And then we have some decision smoothing because, it's basically receiving time series data, and we want to smooth the network predictions a bit. Okay, this is like, again, a simple example for the input path. Specifically, again, remember the previous slide, we want to basically deploy all of this to the ADSP unit, apart from the middle part here, which is going to run on the embedded neural processing unit. So this is, done via this single block here, and I can configure this with the corresponding EAI file. So the font is probably a bit too small, but you just pointed to the location of the EAI file that you generated using the Qualcomm tooling, and that's all you need to do to integrate the AI model into your pipeline. Right, below you can also see you have the option to also give quantization information like minimum, maximum value for inputs and outputs, because we want to run this in a quantized fashion. Okay. So again, this is basically all of the input processing that we're doing with this couple of blocks right here. And there is the output path, and that has things like I talked about before, like the equalizer, a limiter, and others. So this is the classical audio processing that is ideal to run on the ADSP. So this is like designed for it, and there's this remaining component that's really just visualizing some of the outputs. Like you can look at the spectrum contents and trace the outputs of our algorithm. Now we can go ahead and just run this, and this is not yet doing anything related to the hardware. At this point, it's just everything running on my development machine, so my usual laptop or desktop machine. And I can verify that's it's working as expected right there without a need to go to hardware yet at this point. Now it's running about 6 seconds worth of simulation time, and I can verify things like, does it detect the words correctly, my voice commands that are fed in. Okay. So far it's just the development phase. Now we're moving closer to the hardware. The next step would be I could use the simulator environment as a next step before actually targeting the hardware. One way to go there is to go to the apps tab and then search for the corresponding app, run on custom hardware. Again, we can select the simulator, which simulates the hardware, or I could use the actual hardware. And then I can configure some of the settings. So for this specific hardware, what kind of processor version I'm using, for example, down below, whether or not I want to enable some of the optimization libraries like HVX, what version of the eNPU I want to target, and so on. So all of this is easily configurable from this dialog. Right. So there's some more details that are relevant when running this in a process and a loop mode. And here you see the list of available hardwares. I could also go for the Android board, so for the actual Qualcomm hardware. Okay, then there's a setting for the C code generation. Remember, we take this flowchart and translate it over to C code, and one of the most relevant pieces there is turning on the optimization libraries, because we don't want to generate vanilla C code, but we want to generate C code that's optimized for the Hexagon. And this is done via using those libraries provided by Qualcomm, like HVX and QHL, for optimized performance for things like math operations, matrix vector operations, and similar, to get the best possible performance out of our algorithm. For now, we just leave it, go with the QHL library. Yeah, and that's, there's other options you can configure, but, the defaults should be fine. And, we are now ready to actually run this in a pill mode if you want. Again, the workflow with the actual hardware that we have at our booth is exactly the same thing. You just select the hardware instead of the emulator in this case, simulator in this case. So the idea is now I can run a process and a loop simulation and compare the results. That whatever I have designed on my desktop environment is numerically equivalent to what I then see on the hardware. Additionally, I can do things like task profiling to get information about, CPU utilization, runtime of single components within my larger system. So how long does my AI model take? How long does other pre-processing steps take in ticks or nanoseconds on my hardware? And, I can then go ahead and just press this button, and which will do a lot of magic behind the scenes because it will analyze the model, analyze that this is all making sense, translating it over to C code, compiling the C code, downloading it to board, all of that, and running this in a process and a loop simulation. So I'm going to, this takes a couple of minutes, maybe 2 or 3 minutes. That's why I'm fast forwarding and just show the results of this. Right here, once it's completed, it looks something like that. So I get some outputs that tells me the application was actually started and stopped. We see lots of output from the compilers and source code files being generated. And we see also on the right-hand side of the screen the source code files. So here you see that the application was actually running on the simulator. Again, would be the same thing with the hardware. And here we see the corresponding C code files. And if I click on any of those blocks, you will see the corresponding implementation on the C side. So I have this mapping between my simulation environment with the graphical ID and the generated source code files. And we're taking advantage of the optimized libraries, in this case for the calculation of the logarithm with base 10. We see the corresponding library function call in the C code. Right. We also did some profiling. Remember, we turned on the task profiling. So there is a separate UI that collects the runtime metrics from the simulator in this case, or from the actual hardware. And we get information about the execution times of our components or of our algorithm, as well as how much CPU load does this cause. In this case, we're 17%. This is probably the bottom line here, that we're using 17% of the available ticks per clock cycle for this application, while offloading the deep learning network to the eNPU, and the remaining parts of our algorithm are running on the DSP. Okay, we did some benchmarking with this, obviously. There is a simple bar chart here, 3 columns. The red one is just generating standard C code without taking advantage of the eNPU. All of this was tested on, I think it's the same architecture that we have actually at our booth, the same hardware, a Snapdragon 8650. So in the plain C code, we see that this GPU utilization is 250%, which means we cannot complete a step of the algorithm within the available ticks of one cycle. So basically, which means we cannot run this in real time. But once we turn on the eNPU, this drastically improves. It goes down to 55%. And if you further on turn on those optimization libraries that I was talking about, like HVX and QHL, we see those, this is about the same number we saw on the report with the 17% of utilization. So this is generating optimized C code for Hexagon plus offloading the neural network to the eNPU. So this shows the potential of, generating optimized C code. So we're already approaching the end of this presentation. Rajan kicked it off with pointing out the developer experience should be the backbone for successful software and hardware innovations. I was introducing the hardware support package for a streamlined workflow. for algorithm development, including AI deployment, and all of this is enabled via automated C code generation from MATLAB and Simulink. We have obviously lots of resources, documentation, examples around that that are available via QR code. At the heart of it, we want to generate hardware-optimized code, production code, including AI. And the best thing is just visit our booth, check out the demo, come talk to us. And the last word I leave to Rajan.
So I would just like to add what you said. So we have all the resources, but I would like to add yesterday evening, we brought up this demo for the booth from scratch. And some of the issues we ran into were like ADP debug bridge not being the current version or setting the right permissions. But otherwise, any other issues that you saw yesterday, or otherwise it was just the setup issues were pointing to the right.
Some of the issues were due to the fact that the board was very new and we had to do this initial setup.
Yeah, but otherwise, it should be pretty straightforward to start with a setup like this. And we have a lot of resources like MathWorks. Feel free to join us. We have a Discord community, very active. A lot of Qualcomm SMEs are on Discord. So if you have any technical questions on any of the Qualcomm tool chains or just in general, you need help building your app, you can reach out to us on Discord. And if you're interested in future events, there's a couple of barcodes on the screen. Go ahead and pause it, scan it, and you can join us in future, hopefully.
I think that's it. Thank you.
If you have any questions, let us know. We'll stick around. I think we finished a little bit early, but good. Thank you.
Thank you.